Okay, so I will see. We can do up to 3. Well, let's say them they will be bonus quizzes, not added to the average. But well, we already had 9 quizzes. The number of quizzes you have taken will be counted out of 10. We will have at least 1 more. Plus, we might have a few bonus quizzes. What about that? Now, so this is the last week. There is at least one subject which I would like to discuss, the temperature physics, thermal physics. Well, it's a broad topic, and it will not, 1 week, to be frank, 1 week is not enough. So this week will be just a selection of various subjects related with temperature. And you will have a thermodynamics course, unfortunately, at your 4th year. So that is kind of too late. We might change it. You might be taking it in the 3rd year or the 2nd year, probably not, but maybe 3rd year. But well, that is what I would like to do. But if there is anything that you would like us to discuss during the class, during these 5 hours we have left, now we can also discuss that. Now, so we all know what temperature is, right? Do you know what temperature is? You have a feeling. I'm sure all of you have burned your hand sometime early in your life or in your recent times, or felt the cold. And you know that when something is hot or cold, you can feel it. But how do we measure it? Now, in physics, okay, in everyday life, we have a feeling of what is going on. But in physics, what we are supposed to do is quantify the things that we observe in nature, like the hot and the cold. How do we measure temperature? And then you will say, okay, there we have the thermometers, but how does a thermometer work? How do we know that the thermometer measures the temperature? Yes? Change? Okay, so we have these concepts. Temperature. We have the heat, or as your friend put it, energy. And now, your friend tried to answer it, but I have more questions now. What is heat or the energy? So how does, I mean, when I took the thermometer, it is mainly some glass bulb with something at the bottom. It's all our experience that there is a lever over here. It is filled with, well, the mercury thermometers no longer exist. As far as I know, they are also forbidden because mercury is a poisonous substance. Now we have a colored liquid. And what is going on here is as the temperature of this object changes, this separator moves up or down. Now we had already seen a Mercury Barometer. What we had observed in the video was if you fill a tube with the mercury, flip it, immerse it in the mercury, so the mercury just goes down. So the height of this mercury column was around 76 centimeters near the sea level. And the up part is just empty. Now if you look at this diagram, this is kind of similar. All this part is filled with mercury. It has some volume. This is empty. So if you heat it up, what happens is this level of the mercury or the liquid level, it just moves up. So it is just, well, this is not the bottom part is not a pressure, this is not a pressure device. So it is just this height is mainly the measure of the volume of this liquid. So just, if the height is increasing, it is telling us that the volume of this liquid inside is increasing. If the level is going down, the volume is decreasing. Well, it is also a common experience we have that if you heat objects, their size changes. So if you have a ruler of some length L, now when we heat it, we know that its size will increase, This is by delta L. And delta L will be proportional to its original length. And it will also be proportional to the change in the temperature. So this is how we, in a sense, this is how we define the temperature of an object. Or we can measure the change in the temperature by just measuring this difference in the length, this fractional change in the length. Now, a similar relation holds for a volume also. If you have an object that has some volume, it has some initial volume V, and if you heat it up, fixing some corners, if you fix these sides, if you heat it up, it will just become larger. It will have such a shape. And the change in the volume, the fractional change in the volume is again proportional to the change in the temperature of the object. Now, usually these proportionality constants, you can just denote them by this delta L is alpha L delta T. Delta A, you can do a similar thing for the area if you look at, oh, sorry, this goes up also. This is the change in the volume. The area will change by beta A delta T, and the volume will change by, let's say, gamma V delta T. So the change in the area, the volume, or the length of an object will be proportional to the length, area, and the volume of an object, and the change in the temperature with some proportionality constant. And these are all related. Gamma is 3 alpha, and beta is 2 alpha. In fact, we just have a single constant over there, single unknown, single property of the material. Fixed in what sense? Well, it is different for different objects. It's a property of the material, just like the density of an object. And if you tell me which object you are studying, there are tables of these coefficients. I can just go and look up the corresponding coefficient in that table. Of course, these coefficients are can also depend on temperature in general. So this kind of tells us a means of measuring the temperature difference. So in the case of the thermometer, the change in this height over here will be related to the volume change of the liquid all in this region. And so once I measure the change in the height, the volume is kind of fixed. When you are preparing the thermometer, you fix the volume. The volume you know, this you know, and the temperature, the change in the temperature you obtain. Now the gamma, the coefficient gamma here will depend on which unit you use to define the temperature change. Now, when I first see these relationships, to me they kind of didn't make sense. Well, they didn't look consistent. At least this one, these relations and these equalities, they just didn't make sense. My reasoning was this. Let's just imagine a volume, a cube of side length L. So I know that V is equal to L cubed. Now if you heat it, on one side I know that if you heat it, it will become a larger volume. Okay, this will be the new volume, and this will be delta L. I know that delta L is equal to alpha L delta T, delta V is gamma V delta T, but V is equal to L cubed. It should be the L cubed, whatever the temperature is. So if you just put it over there, delta V is the final volume minus the initial volume. Well, the final volume is L plus delta L cubed minus the initial volume is L cubed. And if you just open the parentheses, this is, well, L cubed plus 3 delta L L squared plus 3 delta L squared L plus delta L cubed minus L cubed. And it just didn't look like it was just gamma V delta T. There's no V over there. So what do you think is the problem? So we made some definitions. So here we made some definitions describing the expansion of objects as we increase the temperature. And we had the 3 constants defining these expansions. And somebody claimed that these are all related through these relations, but they just didn't seem to be consistent with each other. So what is wrong? Okay, keep this in mind. Now, why do objects expand as we heat them? As we increase the temperature? Yeah, that's basically the idea. Now, so the first thing we need to understand is what's the solid? What makes an object solid? This is a solid object. We say that this is a solid object. So why is it solid? Because there are atoms making this object, and the atoms are fixed in their position relative to this object. So fixed, in terms of the terminology we are using now, all the atoms here, they feel some kind of a potential energy, and they will be sitting at the bottom of this potential energy. For each one of these atoms, there's kind of an effect. We can define an effective potential energy, and it will be sitting at the bottom, at the minimum of that potential energy. Now, of course, we saw that when we were discussing oscillations, the motion of this object, very close to the minimum, is always like the harmonic oscillator. It vibrates. And quantum mechanics, in fact, tells us that no matter what the temperature is, it will always have some vibration. It will always vibrate. As we increase the temperature, as your friend has pointed out, temperature is related with the energy of the system. What we are doing is we are just increasing the temperature, the vibration energy of this object. Now, if you remember, the energy of an oscillator is proportional to its amplitude squared. So if we increase the energy, it means that we are increasing the amplitude of oscillations. So we are solids. We are 2 atoms in the solid. We are just sitting side by side, just making small vibrations. Then somebody increases our energy, so we start to vibrate faster. So our average separation becomes larger. If our average, imagine this, there are like 10 to the power 23 atoms doing this same thing, and the average separation between any 2 of them is increasing as you increase their energy. So the size of the object is increasing. Thank you. Oh, hold on, Birtan. So what's a liquid? So we have more molecules around. So we are in solids. We are just vibrating. Now, they increase our energy. So we are starting to move faster and faster in random directions, not in harmony like this one. We are just moving in random directions. So at some point, some of them starts to get loose and move to the other side. They slip on top of each other. and then slip to the other side. So this is what we call the fluid, because the atoms making the fluid, they just move around in the fluid. And they increase our temperature further and further. So he just kicks me away. So I'm just free now, independent of them. I can just walk around. Now I'm a gas. So that's basically the 3 phases of the matter. Thank you. And you just give them energy by saying them thank you, and they also evaporate and go to their seats. Now let's be more precise. Okay, so we have an idea of temperature. We know that we can use the expansion of objects to measure the temperature of objects. But which object to use to measure the temperature? Okay, there's these coefficients, alpha, beta, gamma. We have to define them. That is problematic. How do we define them? And we also have to make a definition such that I can use that definition to make measurements here, and my colleagues in Moscow, let's say, they should be able to use the same definition to make the same measurement. And we should all agree what the temperature is. So for that thing, what we use is what we call the ideal gas. Did you study ideal gas in the chemistry classes? Yes, so you already know what the ideal gas is, more or less. Did you follow the chemistry classes? At least I have some, yes. You are supposed to follow them. So what does the ideal gas law tells me? Well, it is measurement. From the experiments, we know that the pressure of a gas times the volume of a gas divided by, let's say, the mole number of the gas times the temperature of the gas. Oh, by the way, before going to the ideal gas, let's go back to our definition of the temperature. So we have this thermometer. And we are measuring temperature using this thermometer. Now we know that V is equal to, delta V is equal to gamma V delta T. Or in this case, by just measuring the height, let's say this is the height, delta H is proportional to delta T. The change in the height will just give me the change in the volume of the liquid. So if I measure the change in the height of the object for a fixed volume of liquid, and then by measuring this height, I directly know what the temperature is, the change in the temperature is. Now I don't want to talk about the temperature of the changes in the temperature, I want to talk about the temperature of object. So if I know the changes in an object, if I want to talk about the volume of an object, I have to put some reference point. How much does the temperature change from my reference point? You know, just like in mechanics when we were talking about the velocity of an object. We said that, velocity is the change in the position. So if we know the velocity and we want to find the position of an object, we first have to choose its position at t equal to 0. At a reference time, where is it? We need to know that. The same thing holds here. So at a reference temperature, what is the height of my object? So what should be that reference point? So what is which point? Okay, there is this guy called Celsius who said that, I have to choose a reference point which I shouldn't have any difficulty in explaining to my friends in Florida. So I should make a definition such that they can also use the same definition. So Celsius decided to use the water. So he took some water right at the freezing point, when you have the ice, and put it in a glass so it starts to dissolve, melt. But there are still some ice and some liquid over there at the same time. So he decided to use that point, that temperature, as the reference point. And he said that, okay, that point I will call, Celsius decided to call 0 temperature. 0 degrees Celsius. Well, the unit of temperature, we also have to define the unit of temperature. So we need another scale, in fact. So again, Celsius just decided that, okay, so he started heating up the water. At some point, it will start boiling. And that boiling temperature, he decided to call it 100 degrees Celsius. So he could call his friend in Florida, say that, hey, look, just take some ice, let it start to melt, and that temperature is 0 temperature. Start to boil the water, and that temperature is the 100 degrees Celsius, so that will be my spacing in my unit of temperature. He called my dear friend in Florida. Okay, here we don't have any difficulty in obtaining ice, so Ankara is cold, so we have the ice freely. There in Florida, they will have a difficulty in obtaining the ice. It is quite hot. So, and well, this is the definition of the Celsius. Then there was some other guy who said, no, I don't like this one. He preferred to call the freezing point of water as 33 degrees Fahrenheit. This is what he preferred to do. And then he wanted to divide this range into 180 units. So he starts with 332 degrees, and this is then 212 degrees Fahrenheit. Does anybody know why this 32 degrees Fahrenheit? Well, he didn't really define this as the 32 degrees Fahrenheit. He just took equal amounts of salt and water, and then he said that, okay, the freezing point of this mixture of salt and water is 0 degrees Fahrenheit. So that was his definition, but let's just say that it is 2 degrees Fahrenheit. Well, some other guy, what is your lucky number? 13, so, okay. So our lucky friend, he didn't like any one of these, so he prefers to call the boiling point, the melting point of water as 13. And another favorite number? 90. And he preferred to divide all this range into 99 equal units. So he said, okay, 13 up to 112. And it is his unit of temperature. You are free to choose your unit. Now, of course, I mean, whichever unit you use, the height of this height, the ratio of the height of that one to the total height, whatever unit you use, should be the same. And that ratio, if I measure in Celsius, Celsius over 100, because I'm dividing that range into equal intervals, Celsius over 100 is equal to Fahrenheit minus 32. This is the proportional to this height. Since I start from 32, whatever I measure here, so I subtract the 32, and that would give me a measure of this height, divided by 180. And this should be equal to your favorite name? Emirjan. 13 degrees E and 112 degrees E. And E minus 13 divided by 99. So whatever unit you like, you just put it over there. And if you have some other favorite numbers, some other names, you can just put it over here. Any questions up to here? Now comes the ideal gas. Now, experimentally, we had observed that if we keep everything constant of an ideal gas, pressure and volume, they are inversely proportional with each other. If you increase the volume of an object, its pressure decreases. If you increase the pressure of an object, the volume decreases. It was also observed that the pressure and the volume, they are both, if you keep volume constant, the pressure will be proportional to the amount of gas you put in your volume. Or if you put the pressure constant, the volume that you have, the gas should have, will be proportional to the amount of volume you have, amount of matter you have. So let's put the N, the mole number, the number of moles. This was constant at constant temperature. Well, this is kind of nice because this allows us, this is the same for all gases also. I mean, in the previous case, the liquid, depending on the liquid we have, the height would have be different because different liquids will be expanding with temperature at a different rate. But in this case, this is true for all ideal gases. Now, before I had to call my friend in Florida, okay, you should build a thermometer such that it is made of such and such a liquid. But here I just call him that okay, use some ideal gas, use some gas. And this ratio is the same, whatever you do. And it is also, this ratio also depends on the temperature. So, and the change in this quantity is proportional to the temperature of the object. So that gives us another means of measuring the temperature. So what we do is get some gas. Fill a tube with some liquid. Well, the liquids are nice. Okay, fill it up completely. Now we know that if this end was at atmospheric pressure, that if you fill this thing with mercury, there will be a height difference between the left arm and the right arm. The height difference will be proportional to the pressure at this point. The height difference is always proportional to the pressure at this point. So you just measure this height of liquid. And well, this height gives you a measure of the pressure inside. Well, since it's a closed system, the number of gas, the quantity of gas inside is constant. Well, you have to make sure that if the volume is constant, also, if N is constant, V is constant, then the pressure would be just a measure of the temperature directly. And the pressure, I can measure the pressure by just measuring this height difference. So I measure this height difference. Since volume and N are constant, the height difference is directly related with the pressure. If I take the height difference, multiply it with the density of the liquid I have, multiplied it with the gravitational acceleration constant. So I get the pressure, but pressure is a measure of the temperature. So in a sense, height in this case will be a measure of the temperature. This is just similar to the previous case. In the previous case, we just use the expansion of a liquid. This is the typical thermometer you have at home. You use the non-electronic ones. They have a colored liquid inside which expands, and you measure the height, and that height gives you the temperature. Now, in this case, we are using a gas. The nice thing about the gas is gases all behave the same, whether you have an oxygen gas or a nitrogen gas, they all behave the same under certain conditions. So you measure the height, that gives you a measure of the temperature. Now there's a few technical difficulties here though. So if you create such a system and heat it up, what will happen is the pressure here will increase, so the height here will increase, so this level will go up and this level will go down. So that is what will happen, right? But if this level of the liquid goes down, it means the volume of my gas is increasing. if I want to make a precise measurement of the temperature, I have to make sure that this level of the liquid is the same, although this height is increasing. But if this height is increasing, whereas this level is fixed, that means the amount of liquid should be increasing. So that is why you add some additional liquid to your system. So all this is filled with your liquid. And you adjust the height of your reservoir such that this level is always fixed. So if you heat this up, this level will try to go down, but then you increase the height of this reservoir up, so it will force more liquid inside. Since it will force more liquid inside, both of these levels will shift up. So the shift down due to the increase in pressure here should be balanced by the shift up due to the more liquid entering here, such that this level will be fixed. Of course, this height will go up. Now, the next question is, how do we define the temperature again? Now, if you use the previous definitions of the Celsius and the Fahrenheit, so let's see. This is the height, this is the temperature. Now, in the previous definitions, what happens is, at the boiling point, at the melting point of the liquid, the water, 0 degrees Fahrenheit. Oh, let me draw. At 0 degrees Celsius, the gases do have some pressure. I mean, today in the morning there were like, the outside temperature was -1 degree Celsius. Now it's probably 0 degrees Celsius. And we all were feeling the atmospheric pressure. Well, we were not feeling it. You would have felt it, the absence of the atmospheric pressure. There's some atmospheric pressure outside, even if we are at 0 degrees Celsius. So that just means that if the gas in this closed chamber So if the gas in this closed chamber was at the 0 degrees Celsius, it just means that it should have some pressure. It has some pressure, it just means that this H, the height difference, is non-zero. So at some 0 degrees Celsius, we have some height. And as we increase the temperature, the observation is that this height increases linearly. Now, we can, of course, use this relation. Well, if you try to extend this line, you will see that experimentally, H is nothing but some constant times T in Celsius units plus 273 plus 15 degrees Celsius. This is the equation of that line. Some constant times T plus the temperature measured in Celsius units plus 273.15 degrees Celsius. So if we are dealing with the Celsius units, we will always have to carry this number with us, around with us. Well, physicists don't like these arbitrary numbers. So rather than using Celsius units, we define another unit, Kelvin. The temperature in Kelvin units is defined as nothing but the temperature in Celsius units plus 273.15 degrees Celsius. So if 0 degrees Celsius, well, this equality is kind of wrong, they are related. They mean the same thing. 0 degrees Celsius is 273 plus 15 degrees Celsius. No, Kelvin. By the way, in Kelvin, you don't have degrees Kelvin. It is only Kelvin. That's the notation. 100 degrees Celsius. This corresponds to 373.15 Kelvin. This is just the Kelvin degrees, in a sense, is just Celsius degrees, but the origin is shifted so that the water freezes at 273.15 degrees. 273.15 Kelvin at standard temperature and pressure. Just the definition. Quiz time. Any questions? At 0 Kelvin, the H goes to 0. Well, I don't understand. Now, you prepare your system and you measure whatever the H is. You are not measuring the changes in the H. You are measuring H. Well, maybe we can discuss in the break.